Data visualization tools. Understanding the data visualization tools of Six Sigma. Introduction. Why data visualization tools matters. In Lean Six Sigma, data visualization tools play a key role in understanding process behavior and driving decisions. They help convert complex data into clear, visual insights that are easy to interpret. From identifying trends to spotting outliers, these tools support root cause analysis and continuous improvement. Visuals like time series plots, control charts, and Pareto charts are commonly used. By making data more accessible, they empower teams to take informed, data-driven actions. Agenda. Here's the agenda for our session. We're going to explore 7 key types of plots that are essential for data analysis and process improvement, especially within a Lean Six Sigma framework. Time series plot. We begin with time series plots. These are used to visualize data trends and patterns over time. They help us understand how a process behaves over a period and identify any recurring cycles or anomalies. Time series charts. Trend analysis. Building on the first, this section highlights patterns and trends in time-based data. It's useful for forecasting and monitoring shifts in performance. Box plot. Next, we'll cover box plots, which are great for displaying data distribution, spread, and outliers. It simplifies complex data into a clean visual summary, allowing for easy comparison across groups. Main effect plot. This chart shows the impact of individual factors on a response variable. It helps us determine which inputs have the strongest influence on outcomes. Interaction plot. Here, we'll explore how 2 factors interact and influence a result. It's particularly important when factors don't act independently, and their combined effect matters. Scatter plot. A scatter plot is used to display the relationship between 2 continuous variables. It helps us assess correlation and whether a potential cause and effect relationship exists. Multivariate chart. Finally, we'll look at multivariate charts, which visualize variation across multiple factors and subgroups. It's ideal for identifying sources of variability in complex processes. Each of these tools offers a different lens for examining data, and together they equip us with the insights needed to drive informed decisions and continuous improvement. Time series plot. Time series plot. One of the most widely used tools for data visualization in process improvement is the time series plot. This plot helps us see how a process performs over time. It's extremely useful for identifying trends, shifts, or cycles in the data. Whether the process is stable, improving, or showing signs of variability. Just like other visualization tools in Minitab or statistical software, the time series plot offers multiple format options based on the type of data and insights you're seeking. As shown in the image, we can create a simple plot for one dataset over time, a plot with groups, where time trends are broken down by categories, multiple plots for comparing different variables side by side, and multiple with groups, where multiple datasets are further grouped, ideal for layered comparisons. Throughout this session, we'll walk through how and when to use these different plot types, and more importantly, how to interpret the patterns they reveal. Options in time series. Plot. When working with time series plots, it's important to choose the right option based on the structure of your data and the kind of analysis you're aiming for. Let's walk through the 4 available options. Option 1. Simple. This is the most basic time series plot. Use it when you have a single numeric dataset over time, like tracking average handling time per day. It's ideal for spotting patterns or shifts in a single process over a period. Option 2. Simple with groups. Use this when your numeric data is paired with a categorical factor. For example, handling time split across different work types. This lets you compare how subgroups perform over time, helping you isolate variation between categories. Option 3. Multiple. Choose this when you want to compare multiple datasets over the same timeline. For instance, comparing handling time data from 3 different months. It helps to see if one period performed better or worse than others. Option 4. Multiple. With groups. This is the most comprehensive view. Use it when you have multiple datasets and a categorical factor, like analyzing handling time for 2 months, broken down by gender or department. This view brings all factors together for richer, deeper insight. Option 1. Making the simple plot. Let's quickly go through how to create a time series plot in Minitab. First, navigate to the Graph menu at the top toolbar, and then click on Time Series Plot from the drop-down. This is the first step in accessing the different types of time-based visualizations available in Minitab. As shown in the screenshot on the right side of the slide, a dialog box will appear. Here, you'll find 4 plot options. Simple, highlighted here, for plotting one numeric variable over time. With groups, for visualizing data over time split by a categorical factor. Multiple, to compare more than one variable across the same timeline. Multiple with groups, when you're analyzing multiple variables and grouping them for deeper insights. For now, we are selecting the simple option, which is most commonly used when you want to look at a single process metric over time, such as daily defect counts or cycle time. Once selected, you'll move to the next window where you can enter your data columns and customize your plot. This tool is very helpful for tracking trends, seasonality, or sudden shifts in your process over time, which is essential for continuous improvement. Creating a simple time series plot. Once you've selected the Simple Time Series Plot option in Minitab, this is the screen you'll see next. On the left, you have a list of available variables from your dataset. These are your columns from the worksheet. Your task here is to select the variable you want to analyze over time. For example, you might choose defects, cycle time, or collection, depending on what you're tracking. In the right-hand field labeled Series, drag and drop or double-click the variable you want to plot. As shown in the transition from the left to the right image, we've selected the variable called Collection. This will now be plotted over time. You can also customize your graph further by clicking on buttons like Time, Scale, Labels, or Display options if you want to adjust axis labels, titles, or formatting. Finally, once you're happy with your selection, you click OK, and Minitab will generate your time series plot. Adding a timestamp to your time series plot. To make your time series plot more insightful and accurate, it's important to link your data to actual time periods. After you select your variable and insert it into the series field, go to the Time Scale button, highlighted in red on the left image. Clicking on this will open a new dialog box, as shown on the right. Here, you want to choose the Stamp option. This allows you to assign a time or date column to your data, so each point on your plot is tied to a specific timestamp. In the Stamp column box, select the column from your dataset that contains the date or time information. In this case, we've selected the column called Date. This step adds clarity to your plot by putting your data in chronological context. It's no longer just a line of values, but a meaningful timeline of how the process evolved over time. Once selected, click OK, and you're ready to generate a time-aware chart. Here's the final output of our time series plot, based on the collection data over time. As you can see on the x-axis, we have the date stamps, which help us track changes chronologically. On the y-axis, we have the actual collection values. This line plot allows us to easily visualize patterns. Notice the peaks and dips occurring at regular intervals. This could indicate weekly cycles or operational fluctuations. The red dots represent actual data points, and the blue line connects them to highlight the overall trend. This type of chart is extremely useful in identifying trends over time, seasonality or repeating patterns, sudden spikes or drops that may warrant investigation. With this plot, we can now ask better questions. For example, what caused the dip in mid-June? Why is there a peak every few days? This kind of visual insight is a great starting point for deeper analysis in any Lean Six Sigma project. Option 2, with groups. Time series plot. Option 2, with groups. Now let's move on to the second option in time series plot, with groups. This option is particularly useful when you want to compare how a process behaves across different categories or groups. For example, you might want to compare average handling time between two different departments, work types, or shifts. In the first window, we select the With Groups option and click OK. The second window that opens allows you to select the series, which is your numeric data, for example, handling time or collection amount. Then, in the box labeled Categorical Variables for Grouping, you'll add the grouping variable, such as department, location, or shift, which breaks the data into categories for comparison. By adding a grouping variable, Minitab will plot separate lines on the same chart for each group. This makes it easier to identify how each category performs over time and spot differences or similarities between them. Once you've selected your fields, you can proceed to add timestamps, just like we did earlier, to make the plot even more meaningful. This is an excellent tool for comparative analysis in Lean Six Sigma projects, helping you isolate factors contributing to process variation. On this slide, we're looking at how to create a time series plot with grouped data using statistical software. This is option 2, with groups, which is helpful when you want to compare trends across categories such as gender, shifts, or departments. On the left-hand window, we begin by selecting the series we want to plot. In this example, collection. Then, under Categorical Variables for Grouping, we can select a variable like gender to group the data accordingly. This allows us to compare the time trends for different groups side by side. Next, we click on the Time Scale button, which brings us to the window shown on the right. Here, we define the time scale. In most cases, selecting the stamp option is best, as it uses actual date-time values for accuracy. Then, we specify the date column as the timestamp, which is essential for aligning our data chronologically. The key takeaway here is at the bottom. Remember to add the timestamp to get more meaningful information. Without a proper timestamp, your time series plot may be misleading or ineffective in revealing patterns over time. This setup ensures we generate clear, segmented insights from our data over time, which is critical in data-driven decision-making. This slide presents the output of a time series plot using option 2, with groups. Here, the variable plotted is collection over time, and we've grouped the data by shifts, namely evening, morning, and night. Each shift is represented by a different colored line: black for evening, red for morning, green for night. The x-axis shows the date, and the y-axis shows the collection values. By visualizing it this way, we can easily compare how each shift is performing across the same time frame. Notice how the evening shift shows a generally increasing trend until mid-January, while the morning and night shifts display more fluctuation. These patterns could help identify operational strengths or areas needing attention in different shifts. This grouped time series plot is valuable for uncovering variations in trends between categories, which would be missed if we plotted only an overall average. Again, this reinforces the importance of assigning a proper timestamp and grouping variable to gain deeper, actionable insights. Option 3, multiple. This slide introduces option 3, multiple, which is used when we want to compare multiple numeric data series over the same time frame. As shown on the left-hand window, we begin by selecting the multiple plot option. This allows us to plot more than one variable on the same time axis, making it easier to visualize and compare trends. On the right-hand side, in the Series field, we enter the numeric columns we want to compare. In this case, Collection Ähnlich and Collection Gaurav. These columns must contain continuous numeric data. The software will then generate parallel plots, so we can examine how each series behaves over time. As always, we need to set the appropriate time scale, where we assign the correct timestamp, usually a date column, to align the data points accurately. This method is particularly useful in performance tracking, such as comparing output from different employees, departments, or systems side by side. This is the output of the time series plot using option 3, multiple, where we're comparing two numeric variables, Collection Ähnlich and Collection Gaurav, over a period of time. You'll notice the x-axis represents the date, showing the timeline. The y-axis represents the collection values. Each variable has a distinct color and line style, black solid for Ähnlich and red dashed for Gaurav, to visually differentiate them. This plot allows us to directly compare trends and fluctuations between the two series. For example, we can observe that while both collections fluctuate, there are periods where one outperforms the other, and times when they align closely. Such visual comparisons help us identify performance differences between individuals or processes, patterns or anomalies over time, periods of consistent or erratic behavior. This method is especially helpful in operational or team performance monitoring, where visual insights lead to quicker decisions. Option 4. Multiple with groups. In this slide, we're discussing the multiple with group option for time series plots in Mini-tab. This option is particularly useful when you have more than one numeric variable, such as different collections made by multiple individuals, and you also have a categorical variable like status or region that groups or classifies this numeric data. As shown in the left-hand image, when you select multiple with groups from the Time Series Plots menu, you're choosing to plot several numeric series at once while using a grouping variable to segment or differentiate the data visually. In the right-hand image, you can see how to configure this plot. Under the Series field, you need to select multiple numeric columns that you want to analyze over time. In our example, Collection Ähnlich and Collection Gaurav have been selected. Then, in the Categorical Variables for Grouping section, you add the categorical data that distinguishes the groupings, in this case, status. This combination allows you to visualize multiple numeric data series across time while still accounting for differences in categorical grouping. It's particularly helpful in process monitoring or team performance tracking across categories like shift, status, or region. This slide shows the output generated from the multiple with group option in the time series plot. As you can see, this plot combines data from two different numeric series, Collection Ähnlich and Collection Gaurav, across a time index. But what makes this plot more insightful is the inclusion of a grouping variable, status, which further categorizes the data into M and L groups. The legend in the top right corner clearly shows how each line corresponds to a combination of variable and status. For example, Collection Ähnlich, M is represented by the solid black line, while Collection Gaurav, L is shown as a dashed blue line with triangles. This visual segmentation allows you to observe and compare trends within each variable and across different status categories over time. This is particularly useful when you are analyzing performance data of different teams or individuals, grouped by status like shift type, region, or work condition, and want to uncover trends or variations in performance. It also helps to quickly identify patterns or inconsistencies among groups, which could guide further investigation or targeted improvements. Trend analysis using time series. In this slide, we are learning how to perform trend analysis using time series data in Mini-tab. To begin, we select Trend Analysis from the Time Series menu, as shown in the screenshot on the right. Once you open the dialog box, you'll notice 4 model types available: linear, quadratic, exponential growth, S-curve, Pearl Reed logistic. It's important to select all 4 models during analysis. Why? Because we want to evaluate which model fits the data best. Mini-tab provides us with 3 statistical measures to evaluate the goodness of fit. 1. MAPE, mean absolute percentage error. 2. MAD, mean absolute deviation. 3. MSD, mean squared deviation. These values are generated for each model and help us compare them. Lower values typically indicate a better fitting model. However, none of these statistics are meaningful in isolation. You should compare the values across the different models and choose the one with the lowest overall errors for your forecasting. Finally, once the best fit model is identified, use it to generate forecasts for your time series data. This slide walks us through the final steps in conducting a trend analysis using time series in Mini-tab. On the left, you'll see the dialog box where you can choose to generate forecasts. Here, you specify how many future time periods you'd like the tool to predict by checking the Generate Forecasts box and entering the number of forecasts you need. Once you've selected the number of forecasts and chosen the appropriate model type, linear, quadratic, exponential, or S-curve, the software will compute future values based on the existing trend. However, generating forecasts is not enough by itself. As shown in the image on the right, it's important to click on the Graphs button and explore the residual plots. Why? Because residual analysis helps validate the model fit. A good model should have residuals that appear random, with no clear pattern. If residuals show patterns or trends, it may indicate that the model is not adequately capturing the data structure. So, to summarize, first, decide how many forecasts you want to generate. Then, always review the residuals to confirm the model's appropriateness before using it for final decision-making or reporting. In this step, we move to the graph settings within the Trend Analysis dialog in Mini-tab. After selecting the appropriate model type and enabling forecast generation, click on the Graphs button, as shown in the left side image. This opens up the Trend Analysis Graphs window seen on the right. Here, we focus on the Residual Plots section. To ensure a comprehensive check on model accuracy, you should select the 4-in-1 option. This setting will generate a set of 4 key residual plots in a single output. 1. Histogram of residuals. 2. Normal probability plot. 3. Residuals versus fits. 4th, residuals versus order. These plots are essential for validating the assumptions of your model. The histogram and normal plot help assess normality. Residuals versus fits. Check for constant variance. Residuals versus order test for independence. Together, these plots give you a clear indication of whether your chosen trend model is a good fit for the data. Always remember, reviewing residual plots is not optional. It's a best practice to ensure your forecast is based on a sound model. This slide introduces the 4-in-1 residual plot, which is a powerful diagnostic tool for evaluating the validity of a trend model in time series analysis. The combined view presents 4 different residual plots in a single window. This layout helps us easily assess whether the assumptions of the model are being met. Let's walk through each of the 4 components. 1. Histogram of residuals O. This helps identify skewness in the data distribution. It also highlights the presence of outliers that may distort the model's accuracy. 2. Normal probability plot. This is used to assess whether the residuals follow a normal distribution, which is a key assumption in many statistical models. O, it can also signal if other variables might be influencing the outcome, or if there are significant outliers. Third, residuals versus fitted values. Plot O. This plot helps check for constant variance, also known as homoscedasticity. OA random scatter suggests the variance is constant, while a funnel shape or pattern indicates issues. O. It also helps detect nonlinear relationships and points out any data that may be outliers. Fourth, residuals versus observation. Order plot. O. This helps identify any systematic patterns over time that might indicate autocorrelation. O. It's especially important in time series analysis because trends in residuals over time suggest the model may be missing a pattern or seasonality. To summarize, this visual output is a crucial step in validating your trend model before using it for forecasting. If you see patterns or violations in any of these plots, you may need to reconsider your model or perform further data transformation. Box plots. This slide explains the components and usefulness of a box plot, also known as a box and whisker plot. A box plot is a graphical tool used to visualize the distribution, central tendency, and variability of a dataset, particularly across categorical groups. Let's break down the elements. Y-axis shows the response variable data. This is the continuous variable we're analyzing. X-axis represents the categorical groups. These could be departments, teams, or time periods. The box itself captures the middle 50% of the data, also known as the interquartile range, IQR. The line inside the box marks the median, or the 50th percentile. It gives us an idea of the central value. Whiskers extend from the box to capture the upper and lower 25% of the data, excluding any outliers. Outliers are shown as asterisks, or circles beyond the whiskers, and indicate data points that lie far outside the typical range. On the right side, we have a visual diagram showing the mathematical basis of these plots. The upper fence is Q3 plus 1.5 times IQR, and the lower fence is Q1 minus 1.5 times IQR. Any data beyond these fences is considered an outlier. The mean and extremes may also be marked in some box plot variations. Why use box plots? They're extremely helpful for comparing multiple groups on the same graph. You can quickly spot differences in medians, data spread, and the presence of outliers. This makes them ideal for both exploratory data analysis and reporting performance trends. This slide guides us on how to access and generate box plots using Minitab. To create a box plot, go to the Graph menu in Minitab. From the drop-down list, select Box Plot, which is highlighted in the screenshot. Minitab allows you to create multiple box plots in a single chart by using a categorical grouping variable. This is useful when you want to compare the distribution of a continuous variable across different groups. For example, comparing customer satisfaction scores across regions or sales performance across different departments. You can also customize the display, add symbols for the mean to see the average values. Show boxes for the median confidence intervals, giving more insight into data stability and spread. This functionality in Minitab supports deeper exploratory data analysis, allowing you to visually inspect data variation, central tendency, and potential outliers, all in one simple plot. This slide explains the different box plot options available in Minitab, depending on how many response variables you're analyzing and whether grouping is involved. Minitab provides 4 main options. 1. 1Y, Simple O. Use this option when you have a single response variable and you want to see a basic box plot without any groups. O, ideal for getting a quick view of distribution and outliers for one set of data. 2. 1Y. With groups, O, choose this when you want to break down the response variable by a categorical grouping. For example, sales data grouped by region. O. This allows you to compare distributions across different categories on the same axis. 3. Multiple Ys. Simple O. Use this to compare multiple numeric variables side by side without grouping. O. Each Y variable gets its own box plot in the same graph, which is great for comparing variables like sales, expenses, and profit. 4. Multiple Ys. With groups OYidion. This is the most detailed view. Use it when you have multiple numeric variables, each categorized by a grouping variable. O, for instance, comparing revenue and expenses across multiple teams or time periods. The screenshot on the right shows how these options appear in the Minitab interface. Selecting the correct option ensures that your visualization is clear, relevant, and aligned with your analysis objectives. This slide demonstrates how to create a simple box plot using option 1Y. Simple in Minitab. On the left side, we see the box plot options window. From here, we choose the simple option under 1Y. This is ideal when you have only one numeric variable and no grouping variable. After clicking OK, the interface shown on the right appears. In this window, you select your numeric response variable, in this case, collection, from the list on the left. Then, move it to the Graph Variables field on the right using the Select button. This plot will generate a single box plot that visually summarizes the distribution of the selected variable. It provides insights into the central tendency via the median line inside the box, the spread of the data through the interquartile range shown by the box, and the presence of any outliers shown as asterisks or dots beyond the whiskers. This is a quick and effective way to check if your data is skewed, has extreme values, or is symmetrically distributed. This slide shows the kind of output you receive when you create a simple box plot in Minitab. The example here is for the variable collection. Let's break down the components of this box plot. Box, interquartile range, IQR. The shaded box in the plot represents the middle 50% of the data. It spans from the first quartile, Q1, to the third quartile, Q3, capturing the central range where most values fall. Median. Inside the box, you see a horizontal line. This line represents the median, Q2, or the 50th percentile, indicating the center of the data distribution. Whiskers. These are the lines extending from either end of the box. O, the lower whisker, extends from Q1 down to the minimum value, excluding outliers. O, the upper whisker, extends from Q3 up to the maximum value, again excluding outliers. Quartiles. O, the bottom edge of the box, marks Q1, 25th percentile. O, the top edge, marks Q3, 75th percentile. This means that half the data lies between these two values. Data distribution. One of the biggest advantages of a box plot is that it visually divides the data into 4 equal parts, each containing 25% of the data set. This makes it easy to understand how spread out or concentrated the values are. This kind of output is essential for quickly evaluating data symmetry, skewness, spread, and identifying potential outliers. It's especially useful in performance analysis, quality control, or any exploratory data review. This slide explains how to use option 2, 1Y, with groups in Minitab to generate grouped box plots. On the left side, you can see the dialog where we select the With Groups option under the 1Y category. This is useful when you want to display the distribution of a numeric variable across different categories or groups. Once you select this option and click OK, the setup window shown on the right appears. Here's how to fill in the fields. Under Graph Variables, choose the numeric column you want to analyze. In our example, it's collection. This is the quantitative data you'll be visualizing. Under Categorical Variables for grouping, select a grouping variable. In this case, we're using shifts. This allows us to break down the collection data by shift. For example, morning, afternoon, and night. By using this option, Minitab will generate separate box plots for each group category side by side, making it easy to compare. Central tendency, spread, IQR, outliers for each group. This view is especially powerful when you want to evaluate variability between teams, time periods, or regions based on categorical segments in your dataset. Well, this slide presents the output from a 1Y with groups box plot, specifically showing collection data segmented by shift, evening, morning, and night. Let's interpret this graph. Each box plot represents the distribution of collection values for one shift category. The center line inside each box is the median, giving a quick sense of the central tendency for each group. The height of each box shows the interquartile range, IQR, the spread of the middle 50% of the data. Wider boxes indicate more variability. The whiskers extend to the minimum and maximum values, excluding outliers, helping us understand the overall range. We can visually compare the shifts. Oh, which shift has the highest median? Oh, which one has more spread or variability? Oh, are there any apparent outliers? In this example, we can quickly compare how the collection metric behaves across different work shifts. This kind of visual comparison is very helpful for managers and analysts who want to evaluate performance consistency across teams or time slots, identify shifts with higher variability or lower collection volumes, make data-driven decisions around resourcing or process adjustments. So remember, when reading grouped box plots, compare medians, IQRs, whisker lengths, and outliers across the categories. This slide presents a comparative analysis of box plot components for 3 different shifts, evening, morning, and night, based on the collection variable. We're breaking down the comparison by each component of a box plot. 1. Whiskers, max and min values. Evening shift shows low variability. The whiskers are shorter, indicating more consistency in collection amounts. Morning shift has the longest whiskers, implying high variability. The spread is wide with a minimum less than 5,000 and maximum near 15,000. Night shift, similar to the evening shift, variability is low, with a more consistent range of values. Second, median. Evening. Median is slightly below 10,000, lower than morning. Morning has the highest median, greater than 10,000, and highest among all 3 shifts. Night. Median is the lowest, slightly below 7,500, indicating lower central performance. 3. Upper quartile, Q3. Q3 is nearly the same across all 3 shifts, showing similar top-end performance for the upper 25% of data. 4. Lower quartile, Q1. Q1 is also similar for evening and morning shifts, indicating a consistent lower range. Night shift has the lowest Q1, reflecting a poorer lower quartile collection performance. 5N. Number of data points. For all shifts, remember that box plots divide the total data points, N, into 4 equal parts, with N/4 in each quartile. You should evaluate the sample size to assess reliability and context of these visuals. Conclusion. This structured view helps compare central tendency, spread, and variability across shifts. Morning shift shows more variability and higher performance, while the night shift lags behind. Evening lies somewhere in between, but with more consistency. This kind of comparative box plot analysis is ideal for performance monitoring, process stability checks, and identifying opportunities for shift-based optimization. This slide introduces Option 3, Multiple Ys, simple for box plots in Minitab. This option is used when you want to display multiple numeric variables side by side in a single box plot. For example, if you want to compare collection, utilization, and RPC values for different teams or departments. However, to use this feature correctly, your data must be in an unstacked format, meaning each numeric variable must be in a separate column. The image on the right demonstrates how to unstack data in Minitab. In the Unstack the Data In field, you select the column containing your numeric values, in this case, collection. In the Using Subscripts In field, select the categorical column that distinguishes different subgroups within the numeric data. Here it's Team Leader. This will result in a separate column being created for each subgroup, e.g., each team leader's collection, effectively preparing the data for a multiple-wise box plot. Once the data is unstacked, select the multiple-wise simple option from the box plot dialog. Then, assign each of the unstacked columns to the Graph Variables section. Minitab will display side-by-side box plots for each variable, making it easy to compare spread, central tendency, and outliers across them. This method is very useful in comparative performance analysis across multiple metrics. This slide provides a visual explanation of the data unstacking process in Minitab, which is essential when using the multiple-wise simple box plot option. In the Unstack Columns dialog on the left, you begin by specifying the column containing the numeric data, in this case, collection. Next, you choose the categorical variable that will be used to separate the data into multiple columns. Here it's Team Leader. By doing this, Minitab will break out the data from the collection column into multiple new columns, one for each unique value in the Team Leader column. On the right side, we see the result of this operation. Each team leader, Anish, Biki, Gaurav, Mohit, Nitin, now has their own separate numeric column. This is the required unstacked format for plotting a multiple-wise box plot, where each team's collection data will be visualized as an individual box. Unstacking is powerful because it allows for side-by-side comparisons of multiple metrics or groups on the same scale. Perfect for performance analysis, benchmarking, or tracking consistency across entities. Make sure to store the unstacked data in a new worksheet to keep your original dataset intact. This slide demonstrates the final step in generating a multiple-wise, simple box plot in Minitab after the data has been unstacked. Once your data is unstacked, as shown in the previous slide, each numeric variable, such as collection Anish, collection Biki, collection Gaurav, and so on, will appear in its own column. In the box plot, multiple-wise, simple dialog, you must select all the numeric columns that you want to compare. These columns are then added to the Graph Variables box. As indicated here, all team-specific collection columns from collection Anish to collection Cha Pankaj have been selected. This setup allows Minitab to plot each variable as an individual box on the same graph, enabling side-by-side visual comparison. This format is especially useful for comparing performance metrics across multiple individuals or departments, identifying who has the highest or lowest spread in data, spotting outliers in specific columns, and generally reviewing variability across multiple sources. It's a great tool for benchmarking and team-wise comparison in business or process performance. This slide presents the final output of a multiple-wise, simple box plot created in Minitab, showing the comparison of collections across 5 individuals: Anish, Biki, Gaurav, Mohit, and Nitin. Let's interpret the plot. Each box represents the distribution of collection data for one team member. The line inside each box indicates the median collection value. The height of the box shows the interquartile range, IQR. how spread out the middle 50% of data is. The whiskers extend to the minimum and maximum values, excluding any outliers. Now, comparing the five. Gaurav has the highest median and a wide spread, suggesting both high performance and high variability. Vicky shows a more compact box, meaning less variability, with a lower median than Gaurav. Anish also has a reasonable spread and a median slightly above Vicky's. Mohit shows a lower spread and lower median, indicating lower and more consistent collections. Nitin appears to have a broader range, similar to Anish, but a slightly higher median than Mohit. This output allows you to visually compare team performance. Identify which team member has more consistent results. Spot anyone with unusually high or low values, although there are no marked outliers in this chart. This kind of comparison is extremely helpful for performance management, trend analysis, and driving decisions on support, training, or recognition. This slide introduces Option 4. Multiple Whys, with groups in Minitab, which is used to create box plots for multiple numeric variables, each grouped by a categorical variable, all on a single graph. On the left side, we select the With Groups option under Multiple Whys. This is ideal when we want to compare how different metrics behave across groups, like comparing collections by different people across shifts. Once you click OK, the setup dialog shown on the right appears. In this window, under Graph Variables, select all the numeric variables you want to analyze, like Anish, Vicky, Gaurav, Mohit, Nitin. Under Categorical Variables for grouping, select your grouping column, which is Shift in this case. This means the plot will display one box plot per combination of numeric variable and group, e.g., Anish, morning, Anish, night, etc. Allow you to compare performance within each person across shifts, or across people within the same shift. Also note the scale level setting. You can choose to display the grouping or graph variables outermost on the axis, depending on what comparison you want to highlight visually. This format is extremely powerful for understanding interactions between variables and groups, such as who performs better in which shift, or which shift has greater variability across the board. This slide shows the output generated when we use Option 4. Multiple Whys with groups in Minitab. In this plot, we are comparing collection performance across two shifts, E equals evening, M equals morning, for 5 individuals, Anish, Vicky, Gaurav, Mohit, and Nitin. Here's how to interpret this grouped box plot. For each individual, there are 2 box plots side by side, one for each shift, E and M. This allows us to visually compare how their performance differs across shifts. Each box plot shows O the median as the line inside the box, O the interquartile range, IQR, represented by the height of the box, O whiskers showing the minimum and maximum values, excluding outliers. Let's look at a few interpretations. Anish has similar medians across both shifts, but the morning shift, M, has more variability. Vicky shows a wider spread in the morning shift, indicating more fluctuation in collection values. Gaurav consistently performs well in both shifts, with high medians and slightly greater variability in the morning. Mohit shows better performance in the evening, both in terms of higher median and narrower spread. Nitin seems to be more consistent across shifts, but the median collection in the morning shift is higher. This graph is extremely valuable for identifying which shift performs better for each person, assessing consistency and variation in performance, making informed decisions on resource allocation or shift assignments. It's important to analyze patterns and anomalies across both dimensions, individual performance and shift effect, to drive effective managerial actions. Main effect plot. This slide introduces the concept of the main effects plot, which is often used alongside ANOVA, analysis of variance, to analyze how different factors influence a response variable. A main effect exists when the mean response significantly changes across different levels of a factor. For example, if average productivity differs across shifts or departments, that indicates a main effect. This plot helps in three key ways. 1. Examine mean responses at each factor level O. It provides a simple line graph where each point represents the average outcome at a specific level of the factor Chi, shift A, B, or CO. This helps in identifying trends and direction of influence. 2. Compare factor level means across multiple factors. You can place several factors side by side, like team, experience, or location, and see which has more impact on the response. This supports multi-factor comparison. 3. Assess the relative strength of effects between factors. The steeper the slope of the line in the plot, the stronger the effect that factor has on the response. Flat lines imply little or no effect, while steep lines suggest a meaningful influence. While the box plot is excellent for displaying data distribution and variability, the main effects plot zeroes in on mean shifts, making it a valuable complement during factorial experiments or DOE, design of experiments studies. This slide highlights three foundational habits that can lead individuals toward financial freedom. 1. Set goals. The journey begins with setting clear financial goals, whether it's saving for a house, retiring early, or becoming debt-free. Goals provide direction and motivation, helping you stay focused and measure progress over time. 2. Budget. Once goals are in place, the next habit is budgeting. This means creating a plan for how you earn and spend money, ensuring your spending aligns with your priorities. Budgeting helps reduce waste, avoid debt, and free up funds for savings and investment. 3. Save. With a solid budget, you can consistently set money aside for the future. This could include building an emergency fund, saving for major purchases, or investing for long-term growth. Saving is the habit that makes your financial goals attainable and your budget purposeful. The illustration on the right represents people engaging in productive habits like analyzing data, tracking growth, and planning actions, further emphasizing the practical, everyday steps toward financial success. Together, these habits form a simple yet powerful framework for anyone aiming to gain control of their finances and build long-term security.